Hello and welcome back to HoloBit. Today we are going to model network dynamics, specifically how individuals connect, interact, and influence one another. We will use the classic SIR model, Susceptible Infected Recovered, as our exercise. This model is famous for disease dynamics, but its principles also apply to how ideas, memes, trends, or financial shocks spread through social networks. But let's be clear, our goal isn't to become epidemiologists. Instead, we are using SIR as a playground to master advanced HoloBit features, such as using links for relationships, create for generating entities, and charts for visualization. We will still follow our analyze, build, and explore framework. However, for complex systems like this, we will practice iterative modeling. Start simple, and then refine it. We will do this step by step visually with no coding required. Ready? Let's dive in. We'll start by breaking down the SIR model. First, the persons. Each individual person can be in one of three states. Susceptible, or S, means vulnerable to infection. Infected, or I, means actively contagious. And recovered, or R, means immune. State transitions depend on the infection rate and recovery rate. Second, the connections, or the network. People don't interact with everyone. They have a circle of contacts. We call the average number of friends the target degree. Infection spreads only along these connections. Third, the system. We need to track the global numbers. How many people are currently infected? What is the cumulative total? Of course, this is only a brief overview. But once we have done this analysis, translating these ideas onto HoloBit becomes almost second nature. We represent the population using an agent entity. Inside, variables define the state, and processes manage the transitions. To model the network, we introduce a new entity, the link. Unlike the spatial grid in our last video, the link is built to model relationships. It explicitly defines who interacts with whom, creating the specific pathways for the virus. At the global level, you'll work with variables on the root canvas to set the core parameters and output statistics. Now let's go ahead and build the basic structure. First, drag an agent onto the root canvas and name it persons. For persons, add a variable named state to store whether they are S, I, or R, and add 4 processes. These will handle initialization, infection, recovery, and data collection. Then drag a link entity onto the canvas and name it contacts. While we are here, let's make it easier to monitor. Under the Tree tab, find Contacts and access its built-in properties. From the drop-down menu, add Population Size by clicking the plus icon. This acts as a live counter, showing you exactly how many connections exist in your network. Next, let's set the rules and data trackers at the global level. Create 4 variables as global parameters: initial infection rate, recovery rate, and target degree. Think of these as your control knobs. Also create 3 variables as global statistics. SIR counts for the totals, current infection rate, and cumulative incidence. Finally, add a network chart to visualize the dynamics. Just like the world view in our previous video, this lets us observe the connections. Here is a pro tip. You can also use text and shapes to organize your canvas layout, making it easier to read. Look, with just a few drags and drops, you have the fundamental structure of the SIR model. Now let's configure the details, starting with the persons agent. Select it. First, set the type to population and the initial number to 300. Open the default appearance settings, change the shape to person, and set the color to blue. Now, how do we assign the starting states to all 300 individuals? The smart way in HoloBit is to automate this using an initialization process rather than manual settings. Let's dive inside. Find the initPersons process. This process needs to run once at the start, so enable the active switch. Then ensure belong to is on individual to let each person execute the setup independently. It will perform two main tasks: creating network links and setting the initial state. Here is the logic flow. First, add a create component named create links, so everyone will try to form connections based on the target degree. Then, add a gateway named assign initial state. Since there are no recovered individuals at the start, we only need to split into two branches based on the initial infection rate. Next, add two compute components, one named setStateI and another named setStateS. Finally, merge them to an end event. Let's configure these components carefully. First, the start event. Keep the default type normal and ensure it is active. Then, the create component. Set the type to new link and choose contacts. This means we are building connections for the contacts entity. For the start point, input self. Think of self as saying me. Since every person runs this process individually, self ensures the connection starts from them, right where they stand. For the end point, input the expression. This tells all individuals in this population, connect to anyone, but don't connect to yourself. Now for the probability. We use a standard network formula here. Simply input the formula, target degree divided by population size divided by 2. Why divide by 2? Because physical contacts are mutual. If A connects to B, B is already connected to A, so we divide by 2 to avoid double counting. Next, the gateway. Keep the default type, exclusive probability. One branch goes to setStateI with a probability equal to the initial infection rate. The other branch goes to setStateS with a probability equal to 1 minus the initial infection rate. Then, for the compute components. Normally, a compute component can execute multiple assignments, like setting the state and the color at the same time. But here is a pro tip. For logic that is used frequently, you should encapsulate it into a reusable process. Let's create this helper process. Create a new process named updateColor. Keep the active switch off and belong to individual. This means it only runs when called, and each one call its own updateColor process. Inside, use a gateway to check the state and add 3 compute components on 3 branches: setColorOrange for S state, setColorRed for I state, and setColorGreen for R state. Finally, merge to an end event to close the process. For the gateway, set it to conditional gateway. Add conditions in sequence. First, if state equals S, go to setColorOrange, else check if state equals I and go to setColorRed, otherwise default to setColorGreen. Then in each compute input, color equals orange, red, or green accordingly. A reusable process to update the color is ready. Now, back in the initPersons process. For setStateI, just keep the formula, state equals I. And for setStates, input state equals S. Then simply add a call component after the compute steps. Set the owner to self and the behavior to update color. Connect the setStateI to it. Done. All set up. Now let's test this setup phase. Zoom out to the root canvas. First, assign initial values to your global parameters, such as 0.1 for initial infection rate, 0.2 for infection rate, 0.05 for recovery rate, and 3 for target degree. Then configure the network chart. Set nodes to persons and edges to contacts. Select Quick Set by Entity Properties to autofill the settings. You can also adjust the visual style, for example, setting the edge curvature to 0 for straight lines. Click Run. You should see a web of nodes. Most are orange, meaning susceptible, and a few are red, meaning infected. Great! The structure is ready. Before we build the complex logic, let's save our progress. Duplicate the scenario and name the new one SIR-fullModel. Now let's get to the core of the SIR model, infection and recovery. We'll first focus on the getInfected process, the transition from susceptible to infected. Only a susceptible person connected to an infected person can get the virus. So, keep the active switch off and belong to as individual. Because getting infected happens to you. It is triggered by an external neighbor, so this process simply waits to be called. Here is the logic flow. First, add a gateway named isSusceptible to check the state. If the state is not S, meaning they are already infected or recovered, go to an end event. If true, continue to another gateway named will-be-infected. This decides whether the individual becomes infected based on the infection rate. If there is no infection, go to the end. If infection occurs, add a compute component to change the state, a call component to change the color, and an end event to close the process. Simple and clear logic. Now let's configure the details. For the start event, keep the default settings. Then, the first gateway. Set the type to condition. Add the condition. State double equals S. If true, go to will be infected. Otherwise, go to end. Next, the second gateway. Keep the type as probability. One branch goes to the compute component with a probability equal to the infection rate. The other branch goes to end with a probability equal to 1 minus infection rate. Now for the compute component. Input the formula, state equals I. Finally, for the call component. Keep the owner as self and set the behavior to updateColor. With this setup, the susceptible to infected transition logic is complete. It waits to be triggered by a neighbor. Next, let's build the spreadOrRecover process, the transition from infected to recovered. An infected individual has two options at each tick: recover or remain infected and try to infect neighbors. First, turn on the active switch and keep belong to as individual. Spreading the virus is an action driven from within. The agent doesn't wait for anyone. It must proactively run this logic every tick. Here is the logic flow. First, add a gateway named isInfected to check the state. If the state is not I, the process closes. So add an end event. If it is I, continue to a gateway named willRecover to check if the individual will recover. Here, we have another two branches. If they recover, they update their state and color and stop infecting others. So add a compute component named becomeR and a call component named setColorGreen. If they do not recover, they try to spread the virus. Insert a find component named findNeighbors to locate targets. Then add a call component named try to spread to infect their neighbors. Finally, add an end event and connect the setColorGreen component to it. Now, let's configure the details. Set the start event to timer, starting from tick 2 and repeating every tick. Why tick 2? Because the agent initializes at tick 1, so this process runs afterwards. For the first gateway, set the type to conditional and add the condition. State double equals I. If true, go to willRecover. Otherwise, go to end. For the second gateway, keep the type as probability. One branch goes to become R with a probability equal to recovery rate. The other goes to find neighbors with a probability equal to 1 minus recovery rate. For the recovery branch, In the compute, input state equals R, and call self's updateColor behavior. For the spreading branch, select the find component. Set the scope using the method getRelatives. Input the expression getRelatives contacts 1 false. It tells the system, look at the contacts link, start from me, go one step out to find direct neighbors, and false means do not include myself. This will find all direct neighbors. What if the agent has no neighbors? If you run the model without handling this, you might see an error saying, find filter result is empty. So open the find component's advanced settings. For boundary, check error. You'll find an error icon on the component. Connect it to the end event. This prevents the model from crashing if a node is isolated. Then for the call, set the owner to find neighbors, which refers to the individuals we just found. Set the behavior to getInfected. This logic says, find my friends connected to me and try to infect them. Logic completed. Now let's do a quick test. Zoom out to the root canvas and click Run. You will observe more nodes in the network turning red and then green as the infection spreads and recoveries occur. We have visual changes. Now we need data. Let's review our variables as global statistics. The first is SIR counts. This is a dictionary type. Why a dictionary? Because we need to store 3 related numbers, S, I, and R, in one package. Important, you can construct this visually by adding 3 entries labeled S, I, and R, using quotation marks. The second is current infection rate, a number reflecting the percentage of people currently sick. The third is cumulative incidence, which tracks the total history of infections. Now, who gathers this data? Let's go to the collectStats process. We don't want every individual shouting their status at once. Instead, we use a collective process. It acts like a global director or a census taker. First, turn on the active, then change the belong to as collective. And you'll notice the icon change on the process. This means it runs actively for the whole population, not for every individual. Inside, add a statistics component named getInfected, followed by an end event. Now let's configure the details. For the start event, set the type to timer, starting from tick 1 and repeating every tick. This ensures we capture fresh data at every step. Then, for the statistics component, set the target to persons.all. We need to count 3 indicators based on the state. Add 3 items. Indicator 1, entity.state equals S. Name it S. Indicator 2, entity.state equals I. Name it I. Indicator 3, entity.state equals R. Name it R. Ensure the method for all is set to sum. Once collected, we need to store and calculate. Under the Compute After Action, input the formulas. Here, this refers to the result coming out of the statistics component. First, store the counts. Simply assign the susceptible, infected, and recovered values captured in this step directly into our global SIR count structure. This keeps our main records up to date. Then calculate the rates. For the infection rate, simply divide the infected count by the total population. For cumulative incidence, we combine infected and recovered cases, then divide by the total population. Data logic is ready. Let's visualize it. Zoom out to the root canvas. For the main SIR curve, simply right-click on the SIR counts and select Chart. Since it is a dictionary, HoloBit automatically generates a multi-line chart showing S, I, and R together. For the rates, right-click on Current Infection Rate and select Chart. To compare it with the cumulative total, go to the Property panel. Find y-axis source and add one more for cumulative incidents from the drop-down. Now you have 2 lines on one chart. Let's run the model. You will see the classic patterns emerge. Susceptibles drop, infections rise to a peak and then fall, and recoveries steadily increase. Specifically, watch the cumulative incidence line climb, while the current infection rate peaks and drops back toward 0. One final critical check. Select the contact's link entity. Ensure it is set to bidirectional. Why? Remember our formula divided by 2? That math assumed that relationships go both ways. If I can infect you, you can infect me. Now let's clear the root canvas. Center the view and collapse the sidebars so we can take a step back and see the full architecture of the network logic you've just connected. Congratulations! You have built a fully functional SIR model. Currently, all individuals act naturally on their own. This is perfect for observing emergence. But for professional simulations, we need to ensure data accuracy, like verifying the network structure and collecting statistics at the exact right moment. So, let's duplicate a new scenario named SIR Explore. In this final section, we will introduce a conductor to organize the execution order. The workflow is global setup, refactoring the agent, the conductor, and visualization. Ready? Let's start with step 1. Global setup. First, we need variables to hold our new data. Create a variable named n and set it to 300. This defines our population size for the persons agent. Create a list variable named current degree. This will store the connection count for every person. Next, step 2, refactoring the agent. Enter the persons agent. We need to stop these processes from acting automatically. First, select initPersons. Simply turn the active switch off. Next, select spreadOrRecover. Turn active off and change the start event from timer to normal. Finally, apply the same settings to collectStats. Turn active off and set start event to normal. Now, all logic is paused, waiting for the conductor. Next, let's give them a new ability, reporting their connection count. Drag a compute component to create a new process named calculateDegree. Input the expression for the compute component. This counts how many friends each person has and reports it to our global list. One last detail here. Click the agent background to open its properties. Remove the fixed initial number, setting it to 0. We will handle creation dynamically soon. Now step 3, building the conductor. Still inside the agent, create a new process named Go. First, let's configure the process itself. Turn on the active and set belong to collective. This ensures this process runs once for the whole group, acting as our conductor. Here is the conductor's sequence. First, creation. Add a create component named createPersons. Confirm the type is new agent, and the agent is current persons, and set the amount to n. Second, initialization. Add a call component. Set the owner to current persons all. Trigger initPersons. This builds the network and assigns the initial states. Third, validation. Add another call component. Target current persons all again, and trigger calculateDegree. Now let's set the timing. Still inside the Go process, add a sub-process named Infection Dynamics. Set its start event to timer, starting from tick 1 and repeating every tick. Inside this sub-process, we define the strict order of events. First, infection. Add a call component. Target persons all to trigger spreadOrRecover. Second, data. Simply copy your statistics component from the old process and paste it here. Finally, close the subprocess with an end event. You have completed the subprocess. Add a final end event for the main go flow. Now the logic is bulletproof. Create, initialize, verify, and evolve. Finally, step 4, visualization and control. Zoom out to the root canvas. Let's verify our new logic. Before starting, add a statistical chart and link it to the current degree list. Run the model. You'll see the standard SIR curves. But look at the new histogram. It proves that your network generation matches the target degree perfectly. Finally, let's make it interactive. Drag a controller component onto the canvas. Link it to the variable n. Set the value type to number and the control type to slider. Then define the range, min 0, max 3000, and set the step to 100. You can do the same settings for other parameters. Now look at this. You have a professional dashboard. You can adjust parameters and restart the simulation instantly. Great work. Let's take a moment to recap our journey. We evolved this model through 3 distinct stages. First, we visualized the network structure. Second, we defined the core dynamics. And finally, we coordinated the entire system with a precise scheduler. You haven't just built an SIR model. You've mastered the workflow of iterative modeling in HoloBit. Now you have a professional simulation sandbox. Go ahead, experiment with different parameters, or try building your own complex systems. HoloBit makes the invisible visible. Thanks for watching, and see you in the next video.